You speak one sentence into a computer. Explain why the sky is blue in one sentence. A moment later, an AI answer appears. What happened between your voice and that answer? Saying the AI processed it hides every useful part of the explanation. Your voice began as a physical pressure change in the air. The microphone produced an electrical signal. The computer stored numbers in memory. Software moved those numbers through several transformations. Somewhere, a CPU, a GPU, or another accelerator executed machine instructions. Here, an accelerator means a processor designed to perform particular classes of computation efficiently. A GPU is one kind. A trained model supplied billions of learned numerical settings. More numbers came out, and the application eventually turned them into text on a screen. The words AI, software, Python, model, and GPU name different parts of this process. They are often placed in one sentence, as if they all do the same job. They do not. We will connect them from the bottom up. We will follow 3 streams. The first is the program, how human-readable code becomes work that a processor can execute. The second is the current data, how a voice becomes numbers, then model input, then an answer. The third is the learned weights created during training. All 3 meet when the model runs. By the end, you should be able to point to where Python stops, where compiled code begins, what the microphone's numbers look like, where those numbers sit in memory, and what a GPU actually receives. If this is the kind of first principles AI lesson you want, tell me which link in the chain you want open next, and subscribe for the rest of the course. One boundary before we begin. This is not a reconstruction of the private internals of ChatGPT, Claude, Gemini, or any other commercial product. Some products process speech locally. Others send audio to remote servers. Some models consume audio directly. Others use a separate speech recognizer first. We will use public, representative systems to make every step concrete, and we will mark the points where real products can differ. Here is the whole lesson in one picture. 3 things meet in a processor. First, there are instructions. Instructions say what operation should happen. Copy these bytes, add these numbers, or multiply these tables of numbers. Second, there is current input data. For our example, the data begins as microphone measurements. Later, it becomes several new numerical descriptions of the sound and the text. Third, there are learned weights. These are numerical parameter values created during training. They help determine how the model transforms its input. The processor follows the instructions. It reads the input data and weights, performs operations, and writes output data. That output is still numbers. Another layer of software may interpret some numbers as scores for possible text pieces. Another may use selected numerical IDs to reconstruct text. A graphic system may interpret other numbers as the position and color of pixels. We will define tokens when the speech model first needs the term. We will return to 3 questions at every layer. What form is the information in now? What rule changes it into the next form? Which component performs that change? Those questions work at every scale, from a microphone membrane to a language model, and from a Python line to a transistor. We will define the more specialized names when we reach them. The bottom of the stack is not Python. It is not machine code either. The bottom is physical hardware. A modern processor contains transistors connected into circuits. For this lesson, you can treat a transistor as an electrically controlled switch. A voltage at one part of the device changes whether current can pass through another part. One transistor is not an AI. A few transistors can form a logic gate. Logic gates can be connected into circuits that add bits, compare values, select between inputs, remember a state, or move data from one place to another. Larger arrangements form registers, arithmetic units, caches, memory controllers, processor cores, and accelerators. A register is a tiny, very fast storage location inside a processor. It holds the values or control information that an instruction is using immediately. We can now name our first complete transformation. The information is represented by physical states in a circuit. The circuit design determines how those states affect the next states. The transistors perform the physical change. People often say that a computer uses ones and zeros. That is useful, but it is shorthand. A logical bit has two distinguishable states, which we label 0 and 1. The hardware may represent those states with voltage ranges, stored charge, magnetic state, or another physical property. 0 does not always mean exactly 0 volts. 1 does not mean 1 universal voltage. The engineering requirement is that the circuit can reliably distinguish the two allowed ranges. The labels 0 and 1 let us reason about the states without calculating transistor physics every time we add two numbers. Consider these 16 bits in memory. 1 1 1 1, 1 0 1 0, 1 0 0 0, 0 0 0 0. Those bits do not carry one automatic human meaning. Read as an unsigned integer. The pattern means 64,128. Read as a signed 16-bit integer using the usual 2's complement convention. The same pattern means -1,408. If the bits are part of an instruction, some may identify an operation and others may identify registers or a value. If they are part of a pixel, groups may represent color channels. If they are 2 bytes of audio data, they may represent 1 microphone sample. The bit pattern stays the same. Its interpretation comes from a format and from the operation that reads it. So everything is ones and zeros does not finish the explanation. We still need to know what the bits represent at that moment and which circuit or program will interpret them. Every processor family defines an instruction set architecture, usually shortened to ISA. The ISA specifies the operations software can request, the registers those operations can use, the data types or widths they support, and the way instructions are encoded. An assembly language instruction might say something like, add R1, R2. In a simplified imaginary machine, that could mean read the number in register 2, add it to the number in register 1, and store the result in register 1. To make the encoding visible, imagine that this machine uses the 16-bit pattern 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0. In this invented format, 0011 is the add operation. 0001 selects destination register 1. 0010 selects source register 2, and the final 4 bits are unused. This is an illustration, not the encoding of any real x86, ARM, RISC-V, or GPU instruction. An assembler turns the symbolic names into the bit pattern defined by that machine's ISA. The real encoding differs across x86, 64, ARM, RISC-V, NVIDIA GPU architectures, AMD GPU architectures, and other processors. When the processor runs, it fetches instruction bytes from memory, decodes the operation, obtains the required operands, executes the operation, and writes a result. Fetch, decode, and execute is the right beginner model. Real processors overlap those stages. They use pipelines, caches, branch prediction, queues, and sometimes out-of-order execution. Several instructions can be at different stages at the same time. The simple model still identifies the essential roles. Instruction bits select an operation, data bits supply operands, and hardware performs a state change. The CPU does not understand the intention behind add. Its circuitry is built so that a valid encoded instruction activates the required control paths. Software is information arranged so that a computer can load and execute it. An installed application usually contains machine code, libraries, resources, configuration data, and metadata. When you launch it, the operating system creates a process, a running instance of the program with its own address space, resources, and execution state. The operating system maps code and data into that address space, allocates memory, and schedules CPU time. The program file on storage is not executing. It is a pattern of bytes stored in flash memory or on a disk. Storage is built for persistence and capacity. It keeps files when power is removed, but the processor does not normally use an SSD as its immediate working surface. RAM is faster working memory for running programs. Caches are smaller and faster again. Registers are smaller still and sit inside the processor. A discrete GPU also has device memory, often called VRAM, that its compute units can access efficiently. The operating system loads or maps the required parts of a program from storage into memory. The CPU begins fetching instructions from an entry point. Keep that distinction in view throughout the lesson. Code on storage is not currently running. Code in memory is not necessarily executing at this instant. An instruction executes only when a processor fetches and performs it. Model weights on storage are not yet active model parameters. Weights loaded into memory are data until an instruction uses them in a computation. Humans rarely write raw machine bytes. We write source code in a programming language. Source code is text. If you open a Python file, a C++ file, or a CUDA source file, the editor displays characters. The file stores encoded character bytes, commonly using UTF-8. For example, the character A is Unicode code point U plus 0041, and UTF-8 stores it as 1 byte, hexadecimal 41, or decimal 65. Other characters can require several UTF-8 bytes. The processor cannot execute those source characters as native instructions. Another program must process the source. A compiler can translate source code into lower-level code, object files, libraries, or a machine code executable. An interpreter can read a program representation and perform the requested operations. A virtual machine can execute an intermediate instruction set. A just-in-time compiler can translate parts of a program into machine code while the program is running. These categories overlap in real systems. Python provides a good example. Suppose you write set answer equal to the result of calling the model on audio. Editors, notebooks, and coding assistants such as VS Code, Jupyter, PyCharm, or Codex may help you create and run that line. None of those tools defines what the Python line means. A Python implementation does. The most widely used implementation is CPython. In CPython, source code is compiled into an internal bytecode representation. The CPython interpreter then executes those bytecode instructions. Python bytecode is not the machine code of your CPU. It is an instruction set for the CPython interpreter. A bytecode operation can tell CPython to load a name, call a function, build a list, or perform another Python-level action. The interpreter itself is a compiled program. CPython's interpreter core is primarily written in C. A C compiler turns that implementation into machine code for a target platform. When you install Python, you normally receive or build that machine code program. When you run a Python file, your CPU executes the installed interpreter's machine instructions. The interpreter reads Python bytecode and performs the corresponding work. Some of that work stays inside the interpreter. A call into a numerical library can quickly leave the Python interpreter and enter compiled C, C++, or accelerator code. At first, it seems to. Python is executed by CPython. CPython was written in C. A compiler compiled the C. What compiled the compiler? Modern compilers can build newer versions of themselves. This process is called bootstrapping. For example, an existing compiler can build a first version of a new compiler. That first version then compiles the compiler source again. A later stage can compile it one more time, and the outputs can be compared as a consistency check. Historically, the chain began with much simpler assemblers, machine code programs, and manually entered instructions. It does not continue downward forever. It stops at machine instructions whose behavior is implemented by processor circuits. When you run Python today, the historical bootstrap is not repeated. The interpreter and libraries already exist as executable machine code. The interpreter does not control the whole machine directly. The operating system decides which process can run, gives it virtual memory, manages files, handles network connections, and controls access to devices. Applications usually call operating system services instead of toggling hardware pins. A device driver is software that knows how to communicate with a specific class of hardware. It translates operating system requests into device operations, configures buffers, submits commands, responds to interrupts, and reports completion or errors. The driver is not a cable. It is software running mainly on the CPU. The physical connection is a bus or interconnect carrying encoded signals between components. In practice, the chain often runs like this: application code, runtime, operating system service, device driver, hardware controller, physical device. The exact chain changes by device and operating system, but those roles explain why a Python function can eventually cause a microphone to start capturing or a GPU to launch work. Python, C++, CUDA, assembly, machine code, and a hardware description language are not competing names for one thing. They operate at different levels and solve different problems. Python lets a person express a large amount of program structure with little text. It is useful for loading data, connecting components, defining model architectures, and controlling experiments or applications. C and C++ give programmers more direct control over memory layout, data structures, operating system interfaces, and performance. Interpreters, frameworks, drivers, and numerical libraries often contain large amounts of C or C++. CUDA is NVIDIA's parallel computing platform and programming model. CUDA C++ lets programmers write host code for the CPU and device functions for an NVIDIA GPU. The CUDA toolchain can compile device code into PTX, which is an intermediate virtual instruction set, and into Cuban files containing binary code for particular GPU architectures. PTX is not the final universal language of all GPUs. If a compatible native binary is available, the runtime can load it. If only suitable PTX is available, the driver may compile it for the installed NVIDIA GPU before launch. AMD and Apple use different stacks. AMD provides HIP and ROCm. Apple provides Metal and Metal performance shaders. PyTorch can select a CUDA backend on NVIDIA hardware or an MPS backend on supported Apple systems. Other accelerators have their own compilers, runtimes, and instruction sets. Assembly language gives symbolic names to low-level instructions and operands. An assembler encodes those instructions as machine code for a particular ISA. Verilog and System Verilog serve a different purpose. Engineers use hardware description languages to describe and verify digital circuits. Chip design tools turn those designs into implementations of hardware. A normal AI request does not pass through Verilog on its way to the GPU. The chip was designed earlier. No language in this stack is more real than another. Each layer gives a person or program a useful vocabulary while hiding details handled below. Imagine that Python requests a matrix multiplication. The Python line calls a framework function. The framework's Python binding enters compiled native code. A dispatcher examines the operation, tensor types, and device. It selects a CPU implementation, a CUDA implementation, an MPS implementation, or another backend. That backend may call an optimized library. The library may launch a precompiled kernel. A graph compiler may combine several operations and generate a new kernel. The accelerator runtime submits commands to a driver. The driver loads compatible device code and schedules it on the hardware. The GPU never reads the original Python characters. Python express the request. Lower layers turn the request into device operations. An AI product is a software system, but the word AI often points to several different objects inside that system. The product includes the interface, account system, file handling, network services, safety checks, tool connections, storage, monitoring, and other ordinary software. The model architecture defines a network of numerical operations. It may include matrix multiplications, convolutions, normalization, nonlinear functions, attention, and other components. The learned weights are arrays of numbers associated with that architecture. The inference engine loads the model, manages memory, selects kernels, schedules work, batches requests, and returns outputs. The hardware performs the calculations. Calling all 5 parts the AI is convenient in casual conversation. It causes confusion when we ask which part was written in Python or which part entered the GPU. Ordinary software can contain explicit rules written by a programmer. If the password is wrong 3 times, lock the account. The behavior comes directly from a condition and an action chosen by the programmer. A learned model also contains human-written software, but programmers do not write one explicit rule for every input the model may encounter. They define a model family, a training procedure, an objective, data handling, and an optimization process. Training adjusts many parameter values so that the model reduces its error on examples. The resulting behavior depends on those learned values. A useful analogy is a machine with many adjustable settings. Engineers build the machine and define how errors will adjust the settings. Training examples pass through it. Each round changes the settings slightly. After many updates, the final settings encode patterns, that help the model transform new inputs. The analogy has a limit. The weights are not independent knobs with simple English labels. A capability is usually distributed across many parameters and operations. Training begins with a model whose parameters have initial values. The model receives examples and produces predictions. A loss function measures error. Backpropagation computes how each parameter contributed to that error. An optimizer uses the gradients to update the parameter values. That cycle repeats over large amounts of data. When training ends, the parameters can be saved as tensors in a checkpoint or another model format. Inference happens later. A runtime loads the model structure and parameter values. A new input enters. The model performs a forward computation and produces an output. During ordinary inference, the base model weights are usually not updated by the user's message. The current conversation can change the model's input context and temporary activations. It does not normally retrain the base model after each sentence. The home map now has all three streams. The program supplies instructions. The current request supplies input data. Training supplied learned weights. Now we can follow the input data from the first physical conversion. When you speak, air pressure varies around its resting level. A microphone converts those pressure changes into an electrical signal. A device that converts energy or information from one physical form to another is called a transducer. That definition tells us the role, but we still need the hardware. Several microphone technologies exist. A dynamic microphone moves a coil in a magnetic field. A condenser microphone uses a diaphragm and a charged plate whose capacitance changes with motion. Phones and laptops commonly use miniature MEMS microphones, although the exact devices vary. MEMS stands for Micro-Electromechanical Systems. A MEMS microphone contains a microscopic movable membrane and a fixed structure. Incoming sound pressure moves the membrane. The movement changes a capacitance. An application-specific integrated circuit, or ASIC, converts that tiny change into a usable electrical output. From here, the microphone interface can follow two common paths. An analog output microphone produces a continuously varying voltage. Other hardware must amplify, filter, sample, and quantize that voltage. A digital MEMS microphone performs more of the conversion inside or near the microphone package. A common output is PDM, pulse density modulation. PDM is a fast stream of 1-bit values. The density of ones over a short interval carries information about signal level. It is not yet the lower rate sequence of multi-bit amplitude values that we normally call PCM audio. The words analog microphone and digital microphone describe the interface presented to the rest of the system. Both begin with a physical membrane moving because of sound pressure. Follow the analog branch first. The microphone transducer produces a small analog voltage. A preamplifier raises that voltage to a level suitable for conversion. The signal then passes through analog conditioning. An anti-alias, low-pass filter limits frequencies above the range that the chosen sample rate can represent safely. A 16 kHz sample rate can represent frequencies below about 8 kHz. Frequencies at or above half the sample rate can fold into false lower frequencies unless they are filtered before sampling. The exact usable band stops short of that theoretical edge because real filters need a transition region. The filtered signal enters an analog to digital converter, or ADC. The ADC performs two conceptually different steps. Sampling chooses moments in time. At a sample rate of 16,000 samples per second, the converter measures the signal every 1/16,000th of a second, or every 62.5 microseconds. Quantization chooses one value from a finite set of levels. A signed 16-bit representation has 65,536 possible bit patterns. They can represent integer values from negative 32,768 through positive 32,767. If the true analog voltage lies between two available levels, the ADC must select a nearby level. The difference is quantization error. The ADC is not recognizing speech. It is measuring voltage. Now, follow a common digital MEMS branch. Inside the microphone package, the MEMS sensor and ASIC convert membrane movement into a 1-bit PDM stream running at a much higher rate than the final audio sample rate. An illustrative fragment might look like this. Do not read that as the binary encoding of one PCM sample. PDM represents the signal through the local density of ones and zeros across many fast pulses. A digital low-pass and decimation filter processes the PDM stream. Low-pass filtering reconstructs the audio band signal and removes high-frequency quantization noise. Decimation keeps samples at a lower rate after filtering. The result can be a multi-bit PCM stream, such as 16-bit samples at 16 kHz or 48 kHz. Depending on the system, this filtering may run in dedicated hardware, a peripheral, firmware, a digital signal processor, or software. Both microphone branches now reach a similar data form, a timed sequence of numerical audio samples. We need a concrete format, so this lesson will use mono-signed 16-bit linear PCM at 16,000 samples per second. Mono means one channel. 16,000 samples per second means one numerical measurement every 62.5 microseconds. Signed 16-bit means each sample occupies 2 bytes and can hold an integer from negative 32,768 through positive 32,767. 1 second, therefore, contains 16,000 sample values. At 2 bytes per sample, 1 second contains 32,000 raw audio bytes. 10 seconds contains 160,000 samples and 320,000 raw bytes. That calculation excludes a file header, metadata, and compression. The numbers are not usually 1, 2, 3, 4, 5. They rise and fall with the measured waveform. To see an exact sequence, use a toy 440 Hz sine wave at 1/4 of positive 16-bit full scale. This is not speech. It gives us clean values that we can verify. For sample index n, we generate each value with round 1/4 times 32,767 times the sine of 2 pi times 440 times n, divided by 16,000. The first 20 samples are 0, 1,408, 2,775, 4,059, 5,222, 6,229, 7,051, 7,663, 8,047, 8,191, 8,091, 7,750, 7,178, 6,393, 5,417, 4,280, 3,016, 1,661, 257, and negative 1,154. If we plotted those numbers in order, they would trace part of a smooth wave. Recorded speech produces a much less regular sequence. A short fragment might contain values near zero during a quiet moment, larger positive and negative values during a vowel, and irregular changes from background noise and consonants. Take the sample value 1,408. As a decimal number, we write 1,408. As hexadecimal, the same bit pattern is hexadecimal 0580. As 16 bits, it is 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0. Those are three written representations of the same numerical value. The computer does not store the four text characters 1, 4, 0, and 8 when it stores a 16-bit PCM sample. It stores 2 bytes containing the sample's binary encoding. Byte order decides which of those 2 bytes appears first in memory. In little endian order, the least significant byte comes first. In big endian order, the most significant byte comes first. A format description tells the software how to reconstruct the value. A negative signed integer is also encoded in bits, commonly using 2's complement. We do not need the full arithmetic here. The important point is that one fixed width bit pattern represents the negative sample according to the signed integer convention. The hardware or file can provide 16-bit integers, but an audio library or model pipeline may convert them into floating point numbers. One common normalization divides each signed 16-bit sample by 32,768. Our sample, 1,408, becomes 1,408. Divided by 32,768 equals 0.0429685. The integer range is then represented approximately around -1 to +1. A buffer might therefore look like this: 0.0000, 0.0430, 0.0847, 0.1239, 0.1594, and so on. The waveform has not become more meaningful. The scale and numerical type changed because floating point values are convenient for signal processing and model computation. Different systems use different sample rates, channel counts, bit depths, layouts, and types. A phone may capture at 48 kHz and later resample to 16 kHz. A Mac audio processing path may use 32-bit floating point PCM. A file may contain compressed AAC or Opus rather than raw PCM. Every buffer therefore needs metadata: sample rate, channel count, sample format, and memory layout. Without that information, a sequence of bytes is ambiguous. These words name different groupings. A sample is one value for one channel at one time. An audio frame contains the simultaneous samples for all channels. A stereo frame has a left sample and a right sample. An uncompressed PCM packet can contain one frame, depending on the format definition. Compressed codecs organize audio into larger coded frames or packets. A model tensor is a multidimensional numerical array. The application may collect many waveform samples into a one-dimensional tensor. A batch adds another dimension. In the layout used by our public specimen, a feature transform turns the waveform into a two-dimensional frequency by time matrix. The physical sound is now long gone. The computer is carrying numerical representations derived from it. It is easy to imagine that the microphone gives audio to a music application and that the application later places it in memory. The order is misleading. An executing application already uses memory for its code, objects, buffers, and state. Live audio reaches the application through memory buffers, managed with help from the operating system and driver. Here is one representative capture path. The application asks the operating system to open an input audio stream with a specified format and buffer size. The operating system and audio driver configure the device. They allocate or map one or more buffers. A buffer is a region of memory reserved for data. The audio controller receives digital sample frames from the microphone or audio codec. In many systems, a direct memory access engine, or DMA engine, transfers sample blocks into a memory buffer without requiring the CPU to copy each sample one by one. The buffer is often cyclic, also called a ring buffer. The hardware writes forward through the buffer. When it reaches the end, it wraps to the beginning and continues. A position value tells the system where the current write point is. Microsoft's WaveRT audio model is one concrete system that exposes a cyclic hardware buffer and position information. Other operating systems organize capture through different APIs and buffer paths. The driver and operating system audio engine notify the application when a block is ready, or make the buffer available through an audio API. The application processes the new block before the hardware overwrites it on a later cycle. Some systems let the audio engine access a hardware DMA buffer directly. Other systems copy data between a driver buffer and a user mode application buffer. The exact path varies, but the data is in memory throughout the software processing stage. RAM contains addressable storage locations. A process usually sees virtual addresses rather than raw physical RAM addresses. The operating system maps ranges of the process's virtual address space to physical memory pages or other backing storage. The application receives a pointer, object, or array view referring to its permitted address range. It does not normally need to know which physical RAM chips hold the bytes. Suppose the application receives a block of 1,600 mono 16-bit samples. That block represents 1/10 of a second at 16 kilohertz and occupies 3,200 raw bytes. The program may read those bytes as an array of signed 16-bit integers. It may convert them to 32-bit floats, which would use 6,400 bytes for the same 1,600 numerical samples. It may append the block to a longer tensor, feed it into a streaming model, or encode it for a network connection. These operations can create additional buffers. The word "the audio" may therefore refer to several numerical copies or views at different stages. The ring buffer solves a timing problem. The microphone produces samples continuously, while application code runs in scheduled bursts. The buffer lets the producer and consumer operate at slightly different moments without losing data. If the consumer falls too far behind, the buffer can overrun. New data arrives before old data is processed. If playback runs out of ready samples, the buffer can underrun. The listener may hear a gap or glitch. None of this recognizes a word. It keeps the numerical stream moving reliably. From memory, the request can stay on the device or leave it. If the speech recognizer and language model run locally, the waveform buffer stays on the device and eventually reaches local CPU, GPU, neural engine, or another accelerator memory. If you use a cloud AI service, your computer may capture and prepare the data, while a remote server performs the main model computation. The GPU running the large model can be hundreds or thousands of kilometers away. Using AI on a laptop does not prove that the laptop's GPU ran the model. The laptop may only be capturing, displaying, and exchanging data with a remote service. An application can send raw PCM, but raw audio uses more bandwidth than necessary. It may first resample, divide the stream into short frames, and compress them with an audio codec. Opus is one public example, designed for interactive speech and audio. It can represent a short audio frame with fewer bits than uncompressed PCM. The result is no longer a direct list of amplitude samples. It is a compressed bit stream that an Opus decoder can turn back into audio samples. Some service interfaces accept PCM directly and define a required sample rate and channel format. Those are interface choices, not properties of AI itself. The application passes bytes to a network library. A secure protocol encrypts the application data. Transport and network protocols divide the data into packets and attach addressing and delivery information. Wi-Fi hardware can encode packet bits into radio signals. Ethernet uses electrical or optical signaling depending on the link. Routers forward packets across multiple networks. At the server, the process reverses the packaging. Network hardware receives signals. Protocol software reconstructs the encrypted byte stream. The secure connection authenticates and decrypts the application data. An audio decoder or parser produces the numerical format required by the server's model pipeline. The audio did not travel through the internet as a tiny waveform drawing. It traveled as encoded bytes, carried by physical signals across a chain of links. A voice-enabled product may run voice activity detection locally. It may reduce noise before transmission. It may transcribe locally and send only text. It may send compressed audio to a speech recognizer. A multimodal model may consume audio directly and produce text or speech. Parts of the work may be split between device and server. Unless the product publishes the design, we should not choose one route and present it as fact. For the next section, we will use a public whisper-style speech recognizer as a concrete example. It is detailed enough to show the numbers changing form. It is not a claim about the product you are using now. Our waveform tensor contains one value for each sampling time. It answers one kind of question. What was the measured amplitude at this moment? Speech recognition often benefits from another view. Which frequency components were present during each short interval? A sustained low note and a sustained high note can have similar overall amplitude. Their waveforms oscillate at different rates. Speech contains mixtures of frequencies that change over time. Vowels have characteristic patterns of frequency energy. Consonants create other transient and noisy patterns. A time frequency representation makes those patterns easier to expose. Suppose the device captured audio at 48,000 samples per second, but the public teaching model expects 16,000. A resampler first applies filtering and then computes a new sequence on the 16 kHz time grid. It cannot safely keep every third sample without filtering, because high-frequency content could fold into lower frequencies and create aliasing. After resampling, 10 seconds of mono audio contains 160,000 waveform values. In the public whisper pre-processing example, the loader pads or trims audio to a 30-second window. Our 10-second request would therefore be followed by 20 seconds of zero-valued padding, creating 480,000 waveform positions. A front end that processed only the unpadded 10 seconds would have about 1,000 hop positions instead of the fixed 3,000 position teaching example used below. In the public Whisper loader, decoded, signed 16-bit samples are converted to 32-bit floats and divided by 32,768. The result is a one-dimensional numerical waveform. One Fourier transform of the whole 10-second recording would tell us which frequencies occurred somewhere in the recording. It would not tell us when they occurred. The short-time Fourier transform solves this by analyzing overlapping windows. In the original public Whisper configuration, audio is sampled at 16 kilohertz. Each analysis window spans 25 milliseconds. At 16,000 samples per second, that window contains 400 waveform samples. The next window begins 10 milliseconds later, a shift of 160 samples. Because the window is longer than the shift, neighboring windows overlap. A hand window smoothly reduces the contribution of samples near each window's edges. This reduces artifacts caused by cutting the waveform abruptly at the window boundary. For each window, the short-time Fourier transform produces complex values for a set of frequency bins. The magnitude says how much of a frequency component is present. Squaring the magnitude gives a power-like quantity used in this front end. The data has changed shape. Before the transform, it was one amplitude value per time sample. After the transform, it is a grid. Frequency bins by time frames. The raw Fourier bins are more detailed than the model needs, and equal frequency spacing does not match the way speech perception is often summarized. A MEL filter bank groups and weights neighboring frequency bins. The original Whisper design uses 80 MEL channels. The later Whisper Large V3 model uses 128. We will keep following the original 80-channel configuration. Each channel collects energy from a band of frequencies with overlapping filters. The public implementation multiplies the MEL filter bank matrix by the squared magnitude or power matrix from the previous step. This is already an example of the same kind of numerical operation used throughout AI. Arrays of numbers multiplied and added according to a fixed rule. The pipeline then takes a base, 1-0 logarithm, after preventing values from falling below a small floor. The logarithm compresses a large numerical range. This implementation also limits the dynamic range to 8 decades below the maximum and applies an affine rescaling before the model receives the values. We will call the resulting matrix the normalized log-MEL spectrogram. For that padded 30-second Whisper chunk, the public implementation begins with 480,000 waveform samples. With a hop length of 160, it produces 3,000 time frames before later model-specific strides. With 80 MEL channels, the teaching input can be shown as an 80 by 3,000 numerical matrix. Only the first part corresponds to our 10 seconds of speech. The remaining columns arise from the padding and boundary effects. Again, those dimensions belong to this public specimen. Other speech systems can use different rates, windows, feature counts, or a learned waveform front end. One column corresponds to a short moment in time. One row corresponds to one MEL frequency channel. One cell is a floating point value derived from the energy in that frequency range during that time window. The matrix might contain values such as, for example, one row might contain 0.42, 0.39, 0.31, and 0.18. Other rows contain different values across the same time frames. These values are illustrative. They are not extracted from our real spoken request. The structure has changed. The microphone produced amplitude over time. The front end produced frequency, energy, over time. The speech model now receives a tensor, not a sound wave in the everyday sense. In a whisper-style encoder-decoder model, an audio encoder processes the log-mel matrix into context-dependent numerical representations. A token is a text unit from a model's finite vocabulary. It may be a whole word, part of a word, punctuation, or another text piece. A text decoder predicts token IDs while conditioning on the audio representations and the tokens selected so far. The decoder produces scores over a vocabulary. A decoding procedure selects token IDs. The tokenizer converts those IDs into text pieces. The pieces join into a transcript. Explain why the sky is blue in one sentence. A system may also predict timestamps, language identity, or whether speech is present. Production systems can add voice activity detection, speaker separation, punctuation, text normalization, and confidence handling. The output text is another representation. It is not a preserved copy of the original waveform. The recognizer estimated a likely token sequence from the audio features and its learned parameters. We now have a transcript, but two parts of the map are still unopened: where the learned parameters were stored and how Python eventually caused a processor to apply them. We will open those parts next, then return to this transcript and follow it into the language model. The model may begin as one or more files on SSD storage. The files contain serialized parameter tensors and metadata. Depending on the format, they may also contain graph structure, tokenizer assets, kernel plans, or other runtime information. Storage keeps bytes when the program is not running. Those bytes do no model computation by themselves. When the service starts, the runtime creates the model structure and loads parameter values. A PyTorch model, for example, can associate layer names with parameter tensors through a state dictionary. A serving engine may use a different, serialized representation. The weights enter system memory, accelerator memory, mapped memory, or a combination. In a common discrete GPU arrangement, the runtime loads model data into host RAM and copies the required tensors into the GPU's device memory. A large service may keep the weights resident so that many requests can reuse them. That discrete GPU layout is common, but not universal. An integrated processor can let CPU and GPU access the same physical memory pool. Some runtimes map files and load pages only when needed. Some inference engines keep part of a large model in host memory and stream weights to the GPU. The safe statement is this: before a compute kernel can use a parameter value, that value must be available through a memory path the executing processor can access. Scale helps explain why many large models run on servers. As a simple size estimate, 7 billion parameter values stored at 2 bytes each require about 14 billion bytes, or roughly 14 decimal gigabytes and 13 gigabytes for the weights alone. Temporary activations, caches, runtime workspaces, and replication can require more memory. This is only a size illustration, not a claim about the model behind any particular product. Imagine a linear layer with a weight matrix of shape 4096 by 4096. If each value uses 2 bytes, that one matrix requires 4096 times 4000. 96 times 2 equals 33,554,432 bytes. That is 32 megabytes for the raw matrix values alone. The matrix does nothing while it sits on storage. A matrix multiplication kernel must read input values and weight values, multiply and accumulate them, and write output values. The model's behavior arises from the combination of architecture, learned parameters, input, numerical precision, and execution procedure. The input tensor contains data for the current request. The weight tensors contain parameters learned during training and reused across requests. Activation tensors contain intermediate results produced while the model is running. An output tensor contains the result of a layer or the final model. During inference, memory may hold all four at once. The runtime can reuse buffers, free intermediates, fuse operations, or move data to reduce memory use. Calling all of these arrays the model data hides important differences. The weights persist across requests. Most activations belong only to the current computation. Consider this representative PyTorch code. Create a CUDA device. Move the model to that device. Move the audio features to that device. Then, with inference mode enabled, call the model on the features and store the logits. The line looks compact because the software stack already contains a great deal of compiled code. CPython first executes Python bytecode for the device object, name lookups, method calls, context manager, and model call. That CPU work decides which Python objects and native functions to invoke. The 2.2 device calls request model parameters and input features on a CUDA device. If a tensor currently resides in ordinary CPU memory, the framework allocates suitable device memory and copies the tensor data. If it is already on the correct CUDA device, a new copy may not be needed. The model call invokes layer operations and produces numerical output such as logits. A separate decoding procedure turns those values into token IDs and text. In an eager PyTorch path, each operator reaches PyTorch's native dispatcher. The dispatcher examines the operation and relevant properties, including the tensor's backend and device. It selects a registered implementation. A CPU tensor might select a CPU kernel. A CUDA tensor selects a CUDA path. An Apple MPS tensor selects an MPS path. Automatic differentiation, automatic mixed precision, and other features can add dispatch behavior. The selected backend may call an optimized library such as CUBLAS for matrix multiplication or CUDNN for supported neural network operations. It may launch a PyTorch kernel. A compiler may fuse a group of operations into generated code. Python is coordinating the operation. The heavy numerical loops are usually in compiled native or accelerator code. Some frameworks run operations as Python requests them. Others build a computation graph first. Modern systems can capture a graph, specialize it for known shapes and data types, combine operations, and compile optimized kernels. A serving engine may not run Python in the request path at all. Python might have been used earlier to export or configure the model. A C++ service can load a compiled engine and handle inference directly. The Python example still holds. It also shows why AI is written in Python is too broad. Python is common in research, training orchestration, and application code. The deployed numerical path can contain C++, compiler-generated code, vendor libraries, device kernels, and machine instructions. The application does not place raw work directly into arbitrary GPU circuits. The accelerator runtime and driver manage a device context, memory allocations, executable modules, streams or command queues, synchronization, and kernel launches. For a CUDA example, the host program can request a memory copy, Launch a kernel with a grid and block configuration and wait for completion. The runtime translates convenient API calls into lower-level driver operations. The driver validates and schedules work for the installed GPU. The CPU writes commands and launch information into memory structures that the GPU can consume. Doorbell registers, command processors, queues, and firmware participate in the handoff, with details that vary by architecture. The physical interconnect carries encoded transactions between host and device. In a desktop system with a discrete GPU, that interconnect is often PCI Express. Some servers use NVLink in parts of the topology. In an integrated system, CPU and GPU can share a package and physical memory, but software still submits work and coordinates access. A CUDA source file can contain CPU host code and GPU device functions. NVIDIA's compiler driver separates the two paths. The host portion is compiled for the CPU. The device portion can be compiled into PTX intermediate code, native Cuban code for selected GPU architectures, or a fat binary containing several options. At runtime, the system chooses a compatible image. If suitable native code exists, it can be loaded. If the package contains compatible PTX instead, the driver can compile that PTX into code for the installed GPU. The GPU eventually fetches device instructions encoded for its architecture. It does not parse the original CUDA C++ or Python text. For a discrete GPU, several categories of bytes may cross the interconnect at different times. Model waits during loading. Input tensors for the current request. Executable device code or compiled kernel modules. Command buffers and launch metadata. Results that the CPU needs to read. Temporary data moved because the runtime cannot keep everything resident. The application does not normally send the decimal characters of each number. It copies binary array storage in a defined data type and layout. Suppose an input feature tensor has shape 80 by 3000 and uses 32-bit floating point values. It contains 240,000 values. At 4 bytes per value, the raw tensor storage requires 960,000 bytes, excluding metadata and alignment. The tensor object also carries or implies information such as device, data type, dimensions, strides, and a pointer to storage. A kernel launch receives addresses or handles and knows how to interpret the storage according to the operations contract. The shapes and types are not usually copied beside every number. They are represented in descriptors, arguments, compiled assumptions, or runtime metadata. A CPU is designed to handle varied work, complex control flow, operating system tasks, and low-latency execution. Modern CPUs also contain vector units and can run AI models well in many situations. A GPU is designed to execute large amounts of similar work in parallel. Neural networks repeatedly apply the same kinds of operations across many elements of vectors, matrices, and higher dimensional tensors. That structure maps well to GPU execution. The distinction is not CPU thinks and GPU calculates. Both execute instructions and calculate. Their architectures allocate hardware resources differently. A CPU usually has a smaller number of powerful general-purpose cores with large caches and sophisticated control. A GPU has many execution resources organized to keep large numbers of threads active and to deliver high throughput on parallel work. A GPU kernel is a device function launched across a grid of threads. Imagine adding 2 arrays with 1 million elements. The kernel program for one thread can be simple. Find my element index. Read A at that index. Read B at that index. Add them. Write C at that index. The host launches enough threads to cover the array. Many threads execute the same kernel instructions on different indices. Neural network kernels are more involved, but the principle survives. Matrix multiplication divides matrices into tiles. Thread blocks cooperate to load tiles, reuse data in fast on-chip memory, perform many multiply-accumulate operations, and write output tiles. Take one output value from a matrix product. The kernel multiplies matching entries from one row and one column, then adds the products. C equals A1 times B1 plus A2 times B2 plus A3 times B3, and so on. That repeated pattern is a dot product. A large matrix multiplication contains many dot products. GPUs divide those outputs among many threads and execution units. Some NVIDIA GPUs include tensor cores, which accelerate supported matrix multiply-accumulate operations in particular data types and shapes. Vendor libraries and compilers can use those units when an operation qualifies. Not every instruction runs on a tensor core. Models also need memory operations, normalization, element-wise functions, indexing, reductions, and control. Other vendors provide their own specialized matrix hardware. The GPU has its own instruction fetch and scheduling machinery. It fetches device instructions, decodes them, schedules groups of threads, reads operands from registers or memory, activates arithmetic or load store units, and writes results. Threads are organized in architecture-specific groups. NVIDIA uses the term warp for a scheduled group of threads. Other vendors use different names and group sizes. Many threads may wait for memory, while other ready threads execute. The scheduler switches among available work to keep functional units busy. The GPU is not executing the Python file one line at a time. The CPU host process used the software stack to submit compiled kernels. The GPU executes those device kernels over tensor data. The device instructions and tensor values are stored as bit patterns in GPU memory, caches, and registers. When an instruction is fetched, control circuits decode its fields. Those fields select operations, source and destination registers, addressing modes, or other behavior defined by the GPU architecture. Clocked circuits move data through registers and functional units. Transistor states change. Arithmetic circuits produce new bit patterns. Memory circuits store the results. At this physical layer, the system is continuous electronics, engineered to behave reliably as digital logic. Timing, voltage margins, capacitance, resistance, heat, and manufacturing limits all matter. The digital abstraction lets programmers work with stable bits and instructions instead of device equations. The AI calculation does not use a special kind of electricity. AI uses an unusual scale and organization of ordinary numerical computation. It is also inaccurate to say that a program simply executes one line after another. The CPU follows program dependencies, but it can pipeline instructions, use several cores, run operating system threads, and overlap work. The GPU runs many threads and can overlap computation with data movement when the hardware, memory, and command streams allow it. Within a model, one layer may depend on the output of the previous layer. That dependency limits the order of the layers. Inside one layer, Thousands of output elements can often be calculated in parallel. During autoregressive language generation, the next token depends on the tokens already selected. Tokens are therefore generated sequentially at the outer loop. The matrix calculations required for each token still contain extensive parallel work. Parallel does not mean every part happens at once. It means independent pieces can execute at the same time, subject to data dependencies and available hardware. Return to the 80 by 3000 log-mel matrix from our public speech example. The input feature tensor is available to the accelerator. The speech model's weights are also available. Compiled kernels implement the model's operations. A kernel reads part of the input activations and a block of weights. It multiplies and accumulates values. It writes a new activation tensor. Later kernels normalize, apply nonlinear functions, mix information across time, or perform other model operations. Layer by layer, the numerical representation changes. The model does not recover the original air pressure. It produces internal activations that are useful for predicting text tokens. The final decoder produces a numerical score for each allowed token. A softmax, or related decoding path, can turn scores into a distribution. The decoder selects a token ID, adds it to the current sequence, and repeats until the transcript is complete or a stopping condition occurs. The GPU returns output data to the host when the application needs it. Depending on the implementation, a small token ID may be copied back after larger operations remain on the device, or more of the decoding loop may run inside an optimized serving engine. It did not receive English speech. It received access to numerical arrays and executable device work. For our speech example, those arrays included audio feature values, model weights, and intermediate activations. The launch information identified kernels, work dimensions, memory addresses, and execution order. The GPU performed numerical transformations. The speech meaning appears at the system level because training shaped the weights and software interprets the final token IDs with a tokenizer. Keeping these layers separate avoids two mistakes. A GPU does not understand language directly, yet calling the result only arithmetic erases the organization and learned parameters that determine what the arithmetic does with speech patterns. Arithmetic is the physical execution mechanism. The learned transformation gives that mechanism its particular behavior. The speech recognizer has produced text. Explain why the sky is blue in one sentence. The chat application now constructs the language model input. It may include system instructions, conversation history, role markers, retrieved documents, tool results, and the user's transcript. A tokenizer converts the text into token IDs. The IDs are integers that index a finite vocabulary. They are not ASCII codes and are not necessarily one ID per word. A toy tokenizer might divide our sentence into pieces such as explain why the sky is blue in one sentence, and a period. Another tokenizer may split the same sentence differently, and each system assigns its own IDs. The pieces here are illustrative, so we will not invent numerical IDs for them. An embedding table converts each token ID into a learned vector. Transformer blocks repeatedly update the vectors through attention, learned projections, nonlinear layers, normalization, and residual connections. A final projection produces scores for possible next tokens. A decoding rule selects one token. The process repeats. Our previous lesson opens that model and follows the matrices in detail. This lesson keeps the LLM as one bounded part of the larger computer system. The surrounding execution path is the same kind we just traced. Token IDs and model weights are numerical tensors. Compiled kernels implement the operations. A runtime and driver submit work. The accelerator executes instructions. Output token IDs return to application software. Suppose the model selects token ID 12,345. The ID is an integer represented in memory with a defined width and byte order. The tokenizer's vocabulary maps that integer to a byte sequence or text piece. The application decodes and joins pieces into Unicode text. The integer 12,345 is not the English word itself. It is an index under one tokenizer's convention. The same integer can mean a different token in another vocabulary. Representation always depends on the agreed format. If the model runs remotely, the server serializes response events as bytes. It encrypts and transmits them through the network connection. Your device receives, authenticates, decrypts, and parses the response. If the model runs locally, there is no server return leg. The local runtime places the output in memory that the application can read, and the two routes rejoin when the application begins rendering the answer. Streaming lets the application display partial output before the server finishes the entire answer. Each event may carry text pieces, token information, audio chunks, tool events, or other structured data depending on the protocol. The network does not know that the bytes contain an explanation of the sky. Routers forward packets according to network headers. The application gives the reconstructed bytes their higher-level meaning. The application now has Unicode text. It chooses a font and a layout region. A text shaping system determines which glyphs represent the characters in context and where those glyphs should be placed. A rasterizer converts glyph outlines into coverage values for pixels. A graphics system blends text color with the background and writes pixel values into a render target or frame buffer. The display pipeline sends pixel data to the screen. Display electronics control millions of subpixels. The subpixels change, emitted or transmitted light. Your eyes receive that light, and your visual system recognizes written language. The final answer has crossed another chain of representations. Token ID, text bytes, Unicode characters, glyphs, pixel values, display signals, light. At each step, a format, a transformation, and an executor connect one representation to the next. A text-to-speech model can convert text tokens and other conditioning information into an acoustic representation. A vocoder, or integrated speech model, produces waveform samples. The application places PCM samples into an output buffer. An audio driver and hardware controller send the samples to a digital-to-analog converter, or DAC. The DAC and reconstruction filter produce an analog electrical signal. An amplifier supplies power to a loudspeaker. The loudspeaker's diaphragm moves the air. The route has returned from numbers to pressure waves. The output chain roughly reverses the microphone input chain, although the hardware and processing are not identical. We can now follow the spoken request without hiding a conversion. Your voice changes air pressure. A microphone membrane moves. A transducer converts that movement into an analog electrical change. In a digital MEMS microphone, an ASIC may convert it into a PDM stream. In an analog path, a preamplifier, filter, and ADC create digital samples. A PDM decimation filter, or PCM-capable audio interface, produces multi-bit sample values. An audio controller and driver place sample blocks in memory buffers, often with help from DMA. The operating system audio service exposes the stream to the application. The application may convert the samples to floating point, change sample rate, reduce channels, suppress noise, or detect speech. For local AI, the numerical audio continues to a local model runtime. For cloud AI, the application may encode audio, encrypt the byte stream, and send it through a network. A remote service reconstructs the audio data. A speech pipeline turns waveform samples into model input. In our public specimen, the input becomes an 80-channel log-mel time-frequency matrix. The speech model executes numerical operations using learned weights and produces text token IDs. The tokenizer converts the IDs into a transcript. The application constructs an LLM input from the transcript and other context. The LLM produces output token IDs one step at a time. The server stream's response bytes back to the device if inference is remote. The application turns the text into glyphs and pixels. The display emits light. A different history created the instructions that move the data. Engineers wrote application code, model definitions, framework code, numerical libraries, runtime code, drivers, and operating system components. Python source was processed by a Python implementation. C and C++ components were compiled for the CPU. Accelerator source, or generated kernels, were compiled into device code. Linkers combined object code and libraries. Installers placed executables and resources on storage. When the application launched, the operating system mapped machine code and data into memory. The CPU executed host instructions. Framework dispatch selected kernels. Runtimes and drivers submitted work. CPUs, GPUs, signal processors, and device controllers executed their own instruction. The instruction route tells the hardware what operations to perform. Before this request, a training system processed examples. Training code defined a model and objective. Hardware executed forward calculations. The loss measured prediction error. Backpropagation computed gradients. An optimizer updated parameter tensors. The final parameter values were saved and later loaded by the inference service. Those values now shaped how audio features became text and how text context became an answer. The learned wait route supplies numerical behavior that programmers did not write as one explicit rule per possible request. Add a processor. Compiled instructions act on current input data and learned weights. That statement works for a CPU, GPU, neural engine, or other accelerator. The exact instruction sets, memory layouts, numerical precisions, and scheduling systems differ. The roles remain stable. Instructions specify operations. Input data represents the current request. Weights contain fitted parameter values from training. Hardware performs the operations and writes output data. Software interprets the output and sends it to the next layer. We simplified transistor behavior into digital switches. Electrical engineers must also handle analog behavior, timing, noise, power, and fabrication. We simplified CPU execution into fetch, decode, and execute. Real processors pipeline, speculate, reorder, cache, and run several operations at once. Some processor architectures decode one machine instruction into smaller internal operations, and some instructions can use microcode. Those are additional layers below the ISA level picture used here. We use two microphone branches. Real devices can combine components differently. We used Microsoft's WaveRT cyclic buffer model as a concrete operating system example. Other audio stacks expose different APIs and buffer paths. We used a whisper-style front-end to expose exact audio numbers. Other speech models may operate on different features or directly on waveform samples. We used PyTorch and CUDA to expose a software-to-GPU path. Other frameworks, graph compilers, serving engines, vendors, and custom chips use different intermediate layers. We also kept the LLM internals short because they were the subject of the previous lesson. The map is not a universal blueprint. It gives you stable questions that reveal how an implementation is organized. A system can capture every sample correctly, transfer every byte correctly, execute every kernel without error, and still produce a false answer. Hardware correctness means the requested computation was performed according to the implemented rules. Model correctness is a different question. The model may have learned incomplete patterns, received insufficient context, selected an unsupported continuation, or been asked for information it cannot verify. Understanding the execution chain explains how an answer was produced. It does not prove that the answer matches reality. AI products are software systems. A model inside the product combines an architecture with learned parameter values. An inference engine runs the model on CPUs, GPUs, or other accelerators. Python is a high-level way to express and coordinate work. A Python implementation executes Python code on the CPU. Framework calls can enter compiled C++ code, optimized libraries, accelerator runtimes, and device kernels. Programming languages differ mainly in the level of abstraction and control they offer. They do not require different laws of physics. Their execution paths eventually reach machine instructions for specific processors. A microphone does not send words into memory. Its transducer turns pressure-driven movement into an electrical signal. Conversion hardware produces timed numerical samples. Drivers and buffers make those samples available to software. The numbers can change form several times. PCM integers, normalized floats, audio features, text token IDs, embeddings, activations, output token IDs, characters, glyphs, and pixels. For cloud AI, the main model may run on a remote GPU. Your local device captures input, transmits encoded bytes, receives output, and renders the result. For local AI, more of the same pipeline stays on the device. At the processor, three things meet: instructions, current input data, and learned weights. The processor produces more numbers. Each higher layer gives those numbers a role. That is how ordinary electrical hardware can participate in a system that recognizes speech and produces language. The intelligence is not a new physical substance inside the chip. It is the behavior of a trained numerical model, executed by a complete software and hardware stack. When you encounter a new AI tool, ask three questions. What form is the information in now? What rule changes it next? Which component performs that change? Those questions will let you place every new term on the map.